So we'll get started with one contributed talk from Eindhoven University of Technology. The talk is entitled Indium Phosphide Temperature Sensor with the Si-CMOS Interface for Photonic Integrated Circuit, and will be given by Thomas Boy. Please.
Thank you very much. Yes. Good afternoon, everyone. Thank you very much for joining us today. I would like to talk to you a little bit about the work that me and some colleagues have carried out in measuring temperature in active integrated circuits for photonics. So, for active integrated photonic circuits, temperature tends to be an actively monitored and controlled variable. And, for example, this would be an example of this, a tunable laser on a metal chuck. Now, the way that we track the temperature is typically done in one of two ways, either off-chip or on-chip. And here I can show you an example of an off-chip measurement. That's the red square over there. It's a thermistor next to the chip. However, this method only gives you limited insight into the local temperature of a structure on the chip. And to give you an example why that is even relevant, let's think about a structure like this, a ring resonator. Now, a ring resonator has a resonant pattern that looks something like this, with regular intervals in the wavelength space. Even with a small increase of temperature, you see a marked displacement of this pattern. And when this structure is part of a larger metastructure, this tends to have an impact on the performance of the overall optical circuit. So, I'm quite interested then in finding on-chip methods for measuring temperature. And the typical way that this has been done in literature is by doing this optically, measuring the temperature through some optical resonance effects. But this neglects the fact that you still need some kind of optical to electrical conversion afterwards, and the fact that you need an external light source typically. So in this work, I would like to show you an on-chip temperature sensor that uses an electrical method on the photonic integrated circuits and does the readout also completely electrically, so you have a digital value that you can work with. So, that's roughly the introduction. I will take you through the design of the sensor, some characterization results, a comparison to the state-of-the-art, and finally draw some conclusions and some design rules as a result of this. So, before we get started, let's talk about what we even consider a sensor. When we measure something with a sensor, we think of a chain like this, where we have some temperature-sensitive elements, a readout circuit, and a computer, what have you. In the photonic integrated circuit literature, this is what people typically call a sensor. It gives you some quantity, typically in the optical domain, that gives you a measure of how hot a certain part of the chip is. In the integrated electronics literature, this is what we typically call a sensor. And since that is my personal background, I wanted to explore an integrated temperature sensor that includes both of these. So I will cover both of these elements, starting with the temperature-sensitive element. And for that, we will be using a so-called electro-optical phase modulator, consisting of this layer stack, of which the principle is based on biasing with a negative voltage. This creates a strong static electric field, and as a result, because of the Pockels or Kerr effect, you will see a modulation of the refractive index of the material, and as a result, a phase shift of the wave that travels through it. But from my perspective, as an electronics designer, I see a diode. So a couple of my colleagues at the Photonic Integration Group at Eindhoven have developed this structure, which is just the same optical structure, but etching a trench around it, so using it just electrically. And now my first question then would be, is this even a diode? Well, yes, we've characterized it, and we found indeed that if you apply a different voltage across it, even though we typically only use it reverse biased, in forward bias, yes, it behaves like a diode. That's very good, of course. But the nice thing that could then come as a result of that is that if we inject a fixed current, you would expect a voltage that depends on temperature. And that is also what we've been able to find naturally. So the voltage here is a function of the thermal voltage, Vt, and the saturation current, Is. And because of the fact that this Is shifts quite a bit from chip to chip, this is a typical method in the electronics literature that is used to have more control over the output of the sensor. By using two diodes, typically of the same size, close together on the chip, and injecting two different currents, we get two different of these V to T slopes. By subtracting these, you end up with a voltage that increases in temperature. Now, this seems like a bit of a roundabout way. Why would you even do this? Well, mathematically, it is kind of nice, because if you subtract these two voltages, you can approximately get a voltage, this delta V, when you assume that these ISs are pretty similar because they're placed close together on the chip, you get a voltage that depends on mostly material quantities, physical quantities, the temperature, and the ratio of currents which you know, you force them. So that is the main principle of operation. Now, if you want to have a well-characterized temperature sensor, we also need to understand what the resolution is. And for that, we need an idea of the noise. Now, what you see here is, of course, a lot of the mains frequencies, so the frequencies that come from the wall, so 50 hertz, 100 hertz. Those are not part of the noise of the diode, but the key result of this is the fact that the noise, the PSD, goes up very strongly when you go to lower frequencies, the so-called 1 over F noise. As a result, if you measure around DC, or in other words, you measure just the voltage that comes out of these two diodes, you will get a very coarse resolution as a result. And that is a challenge that we try to address in the readout circuitry. We are borrowing a technique from electronics called chopping, which works like this. So what I just mentioned, we measure around DC. This is a DC spur around 0. If we now measure the signal and the noise, you'll see that you integrate quite a bit of noise around your signal. Your SNR effectively goes down. But then we place a circuit between these two current sources and diode called a chopper. And it does the following. It's a very simple circuit. Place a low voltage at the input, and the connections will be just as they were before. Place a high voltage at the input of FSW, and you will cross the currents. Now, you will do this in rapid succession, with a square wave typically, and the result of that is that your signal will now be placed at spurs of this switching frequency. And as a result, you will integrate a lot less noise around your signal, because the 1 over F noise goes down as frequency increases. This is the equivalent circuit architecture that we've come up with then. So we have two diodes on the indium phosphide side, two current sources, a chopper, an amplifier chain, and an ADC, an analog to digital converter that allows us to read out the voltage to a computer. So that's the sensor design. Let's talk a little bit about the results. Now the beautiful part, of course, the die pictures. This is a die that we've borrowed from, again, the colleagues from Photonic Integration, an indium phosphide PIC of 2 by 4.6 millimeters, and it contains mostly diodes that we can test of different cross-section and different layer stacks. We've only used the layer stack that I showed before, so we only used half of these diodes. And then finally, the silicon IC, which is only 1 by 1 square millimeter. It is made in 65 nanometer technology, and it contains exactly the blocks that I just described, only with electronics acronyms. So these are the current sources, the amplifier chain, and the ADC. So we characterize this temperature sensor from 0 to 85 degrees, and the power consumption of this overall sensor would be around half a milliwatt for the diode current generation and 140 microwatts for the signal chain. So let's start with the noise first. If we look from the perspective of the electronic chip and we connect only the inputs to ground, we get a noise pattern that looks like the blue curve. If we then connect the photonic diodes, we connect them to the electronic chip, we end up with the red curve. The conclusion of this is that when we place our switching frequency at 1 kilohertz, which is, I don't have an indication here, but you can see it between 10 to the second and 10 to the fourth, we are 1 order of magnitude away in terms of noise from our front end, our circuit. So our measurements will be limited by the diodes. And that corresponds to a resolution of 22 millikelvin for a conversion time of 100 milliseconds. When it comes to the accuracy, these are the output waveforms that you would get as a result of the temperature sweep that we've done. For different diode pairs, you see a systematic nonlinearity and mismatch, and the typical way to then characterize it is to remove the average systematic nonlinearity, because it's shared among all the diodes, and remove the gain and offset, and that leaves you with these residual inaccuracies of around 1.13 degrees Celsius after 2-point calibration from this, in this temperature range. Of course, the most fun thing here would be to apply it to a real circuit. So we've taken a photonic integrated circuit that has a ring resonator just like the one I showed before. This was connected to a photodiode and a fixed wavelength laser. We also had a set of these electro-optical phase modulators on there and a heater. And we applied a square wave of current to this heater. And the wonderful thing for us was that indeed the photodiode and the diode-based temperature sensor, the bottom two graphs, correspond or correlate very nicely with the curve that we saw from the heater. In terms of the state of the art, it's a lot of information, I am aware. I can roughly group all this state-of-the-art here in two categories. On the left-hand side, the optical methods, which are mainly specified in terms of a specificity or sensitivity of a wavelength. The electrical methods are on the right-hand side, where ours is the only method that gives you a digital readout and the full electronic IC characterization as standardized in that literature. So, as a final set of conclusions, this is the first reported diode-based temperature sensor for indium phosphide photonic integrated circuits with a silicon readout EIC. As a take-home message for all of you, you can use diodes, including, for example, EPMs, as electrical tracking methods for the local temperature in your photonic integrated circuits. We reached a resolution of 22 millikelvin at 100 milliseconds and an accuracy of 1.13 degrees with our sensors. And if you want to go ahead and design your own temperature sensors with this, here are some practical considerations. The footprint tends to be quite compact. These are the areas that our sensors used. In terms of the I/O, you need 3 pins, 1 shared ground, and 1 for each of the diodes. And a final hint here is that the accuracy can be strongly limited by the mismatch between the diodes. So it's highly advised to place the diodes in the same orientation close together on the substrate so that you minimize any errors that would be caused by gradients in your litho. These are naturally the references, which can also be found in the proceedings. And that leaves me with a couple of acknowledgements. I would like to thank very much the wonderful people from the Photonic Integration Research Group in Eindhoven. I would like to thank the people from the Integrated Circuits Research Group, specifically Carl van Oosterhout and Atalante Koolen. And then, of course, the Eindhoven Hendrik Casimir Institute for the funding for this project. My name is Thomas Boy. I'm a doctoral candidate in electronic IC design for photonic integrated circuits. Thank you very much for your time, and I'll be happy to take any of your questions that you might have.